Okay, let's continue. So in the last episode, we've seen logistic regression, which was used mostly for binary classification, and it wasn't recommended for multi-class classification or multi-label classification due to there being better alternatives. One of those alternatives is the SVM, the support vector machine, and that's the subject of this episode. So let's say we have two classes that can be separated quite well, which is, of course, an exemplary case. In the real world, these data points may have more overlap. So let's say this is what the training of a logistic regression model came up with, the separating line between the classes, which, as you can see, may be more prone to errors, since, looks like new data points may fall on the other side of the line. So support vector machines are a bit more robust. It applies a few, different ways of finding the best fitting line. It's going to look for the support vectors, which are the data points closest to the decision boundary. Well, this is plural, so of each class, I see a few data points closest, and between that, it's going to draw this margin. Let's take a look at this. So let's say class A blue, class B green. So we've got A to find the optimal separation. It's going to look at the closest ones, draw support vectors. Well, these are the support vectors, but draw these lines, and this is now the maximized margin area to find the optimal hyperplane. We call it a hyperplane because it looks more like a not just a single line, but more like like a multidimensional plane. If you want to go in the mathematics to calculate these lines to find these support vectors and optimize based on that, I left a link down below. I'll also use this link to make the below exercise. And then what you see here is a kernel trick. So let's say the classes aren't that easy to separate, like not by a simple linear function. What they then do is the support vector machine then something called a kernel trick to map the original feature space into a higher dimensional feature space where the classes do become linearly separable. So a Gaussian kernel, you can read more about that on this link. Because we've also already seen polynomial features to make a more complex line for non-linearly separable data points. But this kernel trick is something, the approach the support vector machine can take. Let's go over to the blog post. Let's see, am I zoomed in enough? So this is from Rubik's Code, support vector machines. So the exercise will be about penguins to classify the correct penguins based on the dimensions of the snout. It's going to be either species A or species B, so the Adelie species, or not. So it's binary classification. If they then plotted, they then plot the different species based on the features, and you can see there's a lot of overlap. Some overlap between the Adelie species and the chin strap species, and then some overlap with the Gen 2. If you want to go through all the mathematics and the hyperplane stuff, do read through this. It makes references to logistic regression, but how it operates differently. Then it shows us how to calculate these find these support vectors. Was it again? Pulling the feature space into a higher dimensional feature space, not using the polynomial kernel. let's see, I had a post about the polynomial, which is basically adding features to a higher degree, higher order, to make the well, to find a function that's more complex. So they plot what a more complex function, so like to the third order something, and then they show there's still a lot of species. Well, there's still a lot of overlap that is not being separated that well. Then we've got this RBF kernel, seems to encapsulate more of one species, but yeah, this is a 2D image. Can kind of visualize it as this pulling one species, one class to a higher order feature space, and then trying to separate it in that way. We're talking about different types of SVM, linear SVM and a local deep SVM. This local deep SVM is using that kernel trick. And then we hop over to the implementation. Okay, so we have different species of penguins, the bill length, the bill depth, the flipper length, and so on. You see the species Adelie, Gen2, and Chinstrap, but we're going to do binary classification. So basically, just say if it's an Adelie or not. So we start with just using our ml.net packages. Then we model the data. It's only using the snout length and depth, not the flipper length and so on. And the output is just going to be whether it's should be 1 or 0. The output is this time just going to be true or false, not a probability score. We're going to try multiple SVM models, the linear one and the local deep one. Let's first load in the CSV as a data view. Then we've got a few rows with NA, which means not a number or basically missing values. So we're going to filter those out, those rows, simply using the filter rows by missing values. We're going to find these NAs in this column, so that's why I'm passing that column, but it's going to remove the entire row. Then we do the row count, which should be a little less than the actual, so 342, 345-ish. I'm getting that row count to transform it into a data frame, which we can get a description for and, well, look into it a little more. Let's see, it didn't execute. Okay, that's better. I forgot the var here. And its description, no semicolon if you want to display it in this notebook. So we're just getting the numerical values. We take a look at the min max. We see the max here is about 60. The max here is about 21.5. And the min is also a difference. I'm just saying that because we're going to put this on the same scale between 0 and 1 later in the training process. Take a look at the first 5 records are all Adelies. We'll likely want to shuffle the data. Okay, then the next thing we'll do is replace that Boolean label, which true false, into a 0 and a 1. So if it equals Adelie, it's going to be 1, else 0. If we wanted to do multi-class classification, we'd likely want to categorize those into 0 for maybe Adelie, 1 for the Gen 2, and 2 for the other penguin species. Okay, so now, okay, my mistake. It used to be textual data, the label column, and now it's a simple Boolean true, false. Whether it's Adelie of the Adelie species or not. Okay, then we're gonna do some plotting with our Scott plot. Simply the amount of samples per class. But I have to filter those data frames, make 2 new data frames, one containing all the Adelie samples and one containing the non-Adelie or Adelie samples. Simply doing those filter data frame filters, applying those filters, and then we're going to plot is Adelie, is not Adelie, simply the row count of each data frame. Then we'll see is Adelie is 151 species samples and is not Adelie is 191. So this is important, of course, to know the data balance. Let's say there were 150 is Adelie and only 20 not Adelie. Then the model predicting is Adelie was going to be, it's going to be biased or prone to predict Adelie for any new input sample. We do a train test split because this time we don't have a separate test data set. So we shuffle those and then do the test split because we want the test set to contain a bit of everything, not just the Adelie species samples, not just the last 20 samples, 20% samples. Anyhow, then the row count of the test set is 58. And let's prepare the pipeline. We add the features vector based on the 2 features. And then we normalize min-max. So it's going to put both features on the same scale between the observed minimum and the observed maximum values. The minimum would be 13.1 and the observed maximum is likely the almost 60. So it's going to take that 60, 59.6 is going to be 1. The 13.1 is going to be mapped to 0. So it's scaling it to values between 0 and 1. Let's say we were dealing with images and we'd transform all those images into their pixel values. So the pixel values ranging from 0 to 255, which are the color values. And we'd need to scale those between 0 and 1. We would simply divide by 255. And why we do that is to make the training less computationally heavy, because there's a lot of calculations going on with these values. There's also a few drawbacks, of course, if you're dealing with outliers. So let's say there's data points near the 300 value and all the rest is just between 60 and 1. That's going to skew everything. Or if new data points fall outside of are more than 60, then those are going to be mapped to a value greater than 1, which may have its side effects. Anyhow, therefore, there are also different types of scalars. There seem to be quite a few. Anyhow, let's continue. We start by training a linear SVM to see the performance of that and then compare it to the non-linear variant, which is going to use that kernel trick. So just call it model 1 and then train model 1. Here we have our metrics, which are binary classification metrics. I first check the performance on the test set. The metrics of that, I do need to use evaluate non-calibrated instead of just evaluate method because we're not dealing with logistic regression. So we can't use those logistic metrics or logarithmic metrics. Let's see, the first model is performing, this is the performance on the test set, so the unseen data. Accuracy of 81%. So let's now use another trainer, the local deep SVM, which seems to use a tree depth. I tried both values 3, 5, and 7. But I noticed the higher I put this, the more prone to overfitting, which we should take with a bit of suspicion. It means it overperforms, it learns the data by heart, and the side effect of that could be that it performs poorly on new data. If you want to learn more about this tree depth, it's basically some kind of optimization feature of the local deep SVM compared to the regular multiple kernel. Let's see, so we've got model 2, and down below I see accuracy of 100%. Still, let's see, we are using the test set. So how is it performing so well on unseen data? The test set, of course, is a random sample from the training set, but it is separated from the training set, so it's not like it's seen the test set. But if all the values fall in the range of the training data, maybe it's just overperforming for that data. See, now we've got a 96.55. That's more what we want to see. We don't want perfection on either tests or training. Well, on the training we do want it, on the test we don't want it. So it's general enough to perform on new unseen data. Let's consume the model by using a new sample, creating the prediction engine. I'm using trained model 2, the best one. And it's just going to output true or false and to say is Adélie or not Adélie species. And I added this prediction score. And let's see if that outputs anything, because the probability wasn't giving me anything. This score, oh yeah. Now it gives me 2. Which I'm not sure how to interpret that. So I quickly Googled it. Apparently the score is the distance from the decision boundary, which can be -0 or more than 1 or more than 1. It's just a value, a distance value. Okay, that's all I can tell and show you about support vector machines. They tend to be more robust than the logistic regression for classification tasks because they approach it differently. There are types of support vector machines that are linear, and then there are types that are non-linear using the kernel trick. And the latter seems to perform better than the former when your data is not linearly separable. Big shout out to the Rubik's Code blog post for the explanation, the visualizations, and the exercise. This was again a rather simple classification problem. I've seen this SVM work pretty successfully on an email classification problem, a multi-class classification in which emails would come in on a high frequency, and the SVM classified those, labeled those. For example, an email coming in that is meant to be forwarded to another person would get exactly that label. An email that may be promotional or spam or this or that would get the appropriate label. And just classifying the email based on the textual content so that it ends up in the right inbox or in the right person, or the appropriate task is applied afterwards. So to put it in the spam, to put it in the promo folder, or to have the correct person reply to it, and so on. But maybe that's for one of the future videos. Do make sure to like and subscribe if to not miss out on those episodes. I'll put this notebook on my Patreon, even as on my members only section over here. You can simply become a member to access that. Then do check out my .NET 8 brand website products or subscribe to get these NuGet packages for free.